In order to establish the correct structure of an organic compound, it is necessary to know precisely its molecular formula. The following steps are involved in the determination of molecular formula of a compound. They are: first one, detection of elements, that itself qualitative analysis. Second one, estimation of elements, which itself is quantitative analysis. And third step, the determination of molecular mass. And fourth step, calculation of empirical and molecular formula. Now let us see the first step, that itself is qualitative analysis, which is intended to detect elements. Okay. Most of the organic compounds contain 2 to 5 different elements. The principal elements present are carbon, hydrogen, and oxygen. Less commonly present elements are nitrogen, sulfur, and halogens. In few organic compounds, phosphorus and other metals may also be present. The order of abundance of these elements in organic compounds is given below. Carbon is always present, hydrogen is nearly always present, oxygen generally present, nitrogen, halogens, sulfur less commonly present, phosphorus and metals rarely present. Now let us see the detection of carbon and hydrogen. Carbon is always present in an organic compound and hydrogen too is rarely absent. However, the presence of these two elements is confirmed by the given common test. A small amount of dry organic compound is mixed with about 8 times dry cupric oxide, which is taken in a hard glass tube. The glass tube is clamped and fitted with a delivery tube carrying a bulb in the horizontal length. The end of the delivery tube is immersed in lime water. The bulb of the delivery tube contains anhydrous copper sulfate, which is colorless. The mixture is heated very strongly. Carbon and hydrogen present in the organic compound are oxidized by cupric oxide to carbon dioxide and water respectively. This test itself is also called copper oxide test. Now here you can see the equation. Copper reacts with the copper oxide to form copper and carbon dioxide. It means carbon is oxidized to carbon dioxide. Similarly, hydrogen reacts with copper oxide. Then what do we get? Copper and water. It means hydrogen is said to oxidize to H2O itself. Carbon dioxide turns lime water milky and water vapors turn anhydrous copper sulfate blue. That itself is a test. Then water vapors condense on the cooler part of the tube itself. Calcium hydroxide reacts with carbon dioxide, then it results in the formation of calcium carbonate, okay, which is milky to appear. Similarly, copper sulfate reacts with the water molecules and it becomes hydrous copper sulfate, and which turns into blue color. If the substance under investigation is a volatile liquid or gas, the vapors are passed over heated copper oxide kept in a combustion tube, and the gaseous products are tested as above. If the substance under examination contains sulfur also, the gases evolved are first passed through an acidified solution of potassium dichromate, which absorbs all the sulfur dioxide, and then through lime water, which turns milky. Here you can see the following reactions. Sulfur reacts with copper oxide to form copper and sulfur dioxide, and acidified potassium dichromate further reacts with sulfur dioxide to form potassium sulfate, chromium sulfate, and water. SO2, like CO2, turns lime water milky due to formation of calcium sulfite. Calcium hydroxide reacts with sulfur dioxide to form calcium sulfite and water. Organic compounds supposed to contain phosphorus are heated with oxidizing agents like sodium peroxide. Then the phosphorus present in the organic compound is oxidized to phosphate. Now let us see the detection of nitrogen, sulfur and halogens. These elements are tested in an organic compound by Lassane's test. The organic compound containing nitrogen, sulfur, or halogens is fused with sodium metal as to convert these elements into ionizable inorganic substances. That is, nitrogen into sodium cyanide, sulfur into sodium sulfide, and halogens into sodium halides. Na plus C plus N, it becomes sodium cyanide. Na plus S, it becomes sodium sulfide. Na plus halogen, it becomes sodium halide. Here X may be chlorine, bromine, or iodine. Sodium metal should be in slight excess, otherwise, in compounds containing nitrogen and sulfur together, sodium thiocyanate is formed, which gives red color with the ferric ions. With excess of sodium, the thiocyanate formed decomposes into cyanide and sulfide. Now, the cyanide, sulfide, or halide ions can be confirmed in the aqueous solution by usual tests. The aqueous solution is called Lassane's filtrate. Instead of sodium metal, mixture of sodium carbonate and zinc can be used. It is called Middleton's fusion method. Now let us see the preparation of Lassane's filtrate. A small piece of sodium of pea size is freshly cut and dried between the folds of filter paper. Then it is taken in a fusion tube, that itself is ignition tube, and heated gently. When it melts to shining globule, the tube is removed from the flame and a small amount of organic compound, which is 0.05 grams of solid or 3 to 4 drops of liquid, is added to the sodium. The tube is first gently heated till the reaction ceases and then strongly heated till it becomes red hot. It is now plunged directly into 10 to 15 ml of distilled water, which is taken in a porcelain basin and crushed by the tip of the tongs. The contents are heated for 5 minutes and then filtered. Now the filtrate is known as Lassane's filtrate or sodium extract. Organic compounds, being covalent, normally do not have ionizable groups. Hence, direct test is not possible. Now let us see detection of nitrogen. 2 ml of Lassane's filtrate or sodium extract is taken in a test tube and 2 or 3 drops of freshly prepared ferrous sulfate solution is added. As the solution is alkaline, excess of sodium reacts with water to form sodium hydroxide and the solution is said to be alkaline. A green precipitate of ferrous hydroxide appears. The mixture is boiled for 2 minutes, cooled and acidified with dilute sulfuric acid. H2SO4 dissolves ferrous hydroxide. Appearance of green or Prussian blue color confirms the presence of nitrogen. Alternatively, ferric chloride and dilute hydrochloric acid may also be added. Now, chemistry of the test. Lassane's filtrate consists of sodium cyanide and sodium hydroxide. Na plus C plus N, on heating it becomes sodium cyanide. Na plus H2O, NaOH plus H2. When the filtrate is boiled with ferrous sulfate solution, the following reactions take place. Ferrous sulfate reacts with sodium hydroxide to form ferrous hydroxide, which is green in color, and sodium sulfate. Now this ferrous hydroxide further reacts with sodium cyanide to form sodium ferrocyanide, which is sodium hexacyanoferrate 2 and sodium hydroxide. At the same time, some ferrous sulfate is converted into ferric sulfate. This reacts with the sodium ferrocyanide to form ferric ferrocyanide or iron 3 hexacyanoferrate 2, which gives Prussian blue color or precipitate. Now you can see the reaction. In case ferric chloride is added, the following reaction occurs. Sometimes when the amount of nitrogen present is small, the Prussian blue is present in colloidal form and the solution looks green. When the alkaline solution is acidified with HCl, the yellow color of ferric chloride produced by the acid. When the alkaline solution is acidified with HCl, The yellow color of ferric chloride produced by the acid with the ferric ions makes the blue color to appear as green. When the organic substance contains both N and S, sodium thiocyanate is formed, which gives a blood red coloration of sorry, uh, blood red coloration of ferric sulfocyanide or ferric thiocyanate with ferric ions. Okay. But this test fails in case of diazo compounds. Now let us see detection of sulfur. Last science test, first one. Sulfur is present in sodium extract in the form of sodium sulfide. When sulfur and nitrogen both are present, sodium thiocyanate is formed. Both are tested simultaneously with ferric chloride solution when a blood red coloration appears. Sulfur is tested in the sodium extract in the following manner. To a little of sodium extract, freshly prepared solution of sodium nitroprusside is added. A deep violet color indicates the presence of sulfur. Here you can see the reaction. Sodium sulfide reacts with sodium nitroprusside to form violet colored complex, which is sodium thionitroprusside or purple color complex. To another test portion of sodium extract, a few drops of acetic acid and lead acetate are added. A black precipitate of lead sulfide will be formed. To a small portion of sodium extract, a few drops of acetic acid and cadmium acetate are added. Then yellow precipitate of cadmium sulfide will be formed. Now second one, oxidation test. Sulfur can also be tested by oxidation test. The organic compound is fused with the fusion mixture, which is a mixture of sodium carbonate and potassium nitrate. The sulfur, if present in the organic compound, is oxidized to sodium sulfate. Na2CO3 reacts with sulfur and oxidized to sodium sulfate. The fused mass is dissolved in water and the solution is acidified with hydrochloric acid. Then barium chloride solution is added. The formation of white precipitate of barium sulfate indicates the presence of sulfur. Right. Na2SO4 plus BaCl2 gives rise to white ppt of barium sulfate and NaCl. Now let us see detection of halogens. First one, Lassen's test. Chlorine, bromine and iodine are present in the sodium extract in the form of sodium chloride, sodium bromide and sodium iodide respectively. For the test of halogens, it is necessary to remove sodium cyanide and sodium sulfide from the sodium extract if nitrogen and sulfur are present. This is done by boiling the sodium extract with concentrated nitric acid. NaCN plus HNO3 gives rise to NaNO3 plus HCN, hydrogen cyanide gas is released. Similarly, sodium sulfide reacts with the HNO3 to form sodium nitrate and H2S gas. Gases will escape out. If sodium cyanide and sodium sulfide are not decomposed, white or black precipitate of silver cyanide and silver sulfide respectively are formed with the silver nitrate solution. Hence, initially we have to boil the sodium extract with concentrated nitric acid to remove sodium cyanide. It is as HCN to remove sodium sulfide as H2S. Right. To the sodium extract, which is free from sodium cyanide and sodium sulfide, silver nitrate solution is added after acidifying it with dilute nitric acid. Appearance of white precipitate of silver chloride or pale yellow precipitate of silver bromide or yellow precipitate of silver iodide indicates the presence of chlorine, bromine or iodine in the organic compound respectively. NaCl reacts with the silver nitrate to form white ppt of silver chloride, which dissolves in ammonium hydroxide. Sodium bromide reacts with the silver nitrate to form pale yellow ppt of silver bromide, which is sparingly soluble in ammonium hydroxide. Sodium iodide reacts with the silver nitrate to form yellow ppt of silver iodide, which is insoluble in ammonium hydroxide. Chlorine water test for bromine and iodine. From the color of silver bromide and silver iodide, it is difficult to judge whether the organic compound contains bromine or iodine. To confirm the presence of bromine or iodine, the above test is supplemented by chlorine water test, which is also called layer test. A small portion of sodium extract is acidified with the dilute HNO3 or H2SO4, and then 1 ml of chloroform or carbon tetrachloride is added. Then it is to be shaken vigorously with excess of chlorine water. If chloroform layer becomes yellow or brown, bromine is present, and if violet, iodine is present. Sodium bromide reacts with chlorine to form sodium chloride and bromine. Bromine turns CS2 layer orange. Bromine dissolves in chloroform or CCl4, giving yellow or brown color layer. Sodium iodide reacts with chlorine to form sodium chloride and diiodine, which turns CS2 layer violet. I2 dissolves in chloroform or CCl4, giving violet color layer. The presence of NaCN or Na2S in sodium extract does not interfere in this test. Now the next one is Beilstein test or copper wire test. The copper wire is flattened at one end. The flattened end is heated in an oxidizing flame of the burner till it ceases to impart any green or blue color to the flame. A small quantity of organic substance is taken on the flattened end of the wire and introduced into the flame. A green or blue color of the flame indicates the presence of halogens. The green or blue color is produced due to interaction of halogen with copper to form volatile copper halides. Note, this test, though very sensitive, is not always reliable. Substances which do not contain halogens such as urea, thiourea, pyridine, quinoline and purines etc. also impart color to the flame. Now let us see detection of phosphorus. The organic compound is fused with the fusion mixture, which is a mixture of sodium carbonate and potassium nitrate or sodium peroxide. The phosphorus present in the organic compound is converted into sodium phosphate. The fused product is extracted with water and aqueous solution obtained is boiled with concentrated nitric acid and ammonium molybdate. A yellow precipitate or coloration indicates the presence of phosphorus. The yellow precipitate is due to the formation of ammonium phosphomolybdate. NH4 taken thrice, PO4.12 MoO3. You can see the reactions. Sodium phosphate reacts with nitric acid to form phosphoric acid, sodium nitrate, and this phosphoric acid further reacts with ammonium molybdate in the presence of nitric acid to form ammonium phosphomolybdate, which is yellow PPT. Now let us see detection of oxygen. There is no satisfactory qualitative method for the detection of oxygen. However, its presence can be inferred indirectly. First one, if the organic compound is heated alone in a dry test tube in presence of nitrogen, the formation of water drops on cooler parts of the tube may indicate the presence of oxygen. Second one, the presence of oxygen can be inferred by testing the presence of functional groups known to have oxygen. Example, hydroxyl group, aldehyde group, carboxyl group and nitro group, etc.